Hey everyone, welcome back to the channel and this statistics playlist series. In the last video, we explored about the percentile, quartiles, phi number summary, and how to construct the box plot manually. In today's video, we will be taking things a step further. We will be breaking down the concepts of covariance, what it is, why there was need of covariance when there is variance existence, and and how to understand it visually and graphically. Then we will be looking into the correlation. What is the main difference between the causation and correlation, which is one of the most important concept in the stats to understand. So let's get started with the covariance. So in the last video, we studied about the variance, where variance is the spread of the data relative to the mean of the data. How much, if this is the data, if this is the mean, how much there is spread of the data with relative to the mean of the data. The greater the spread, greater the variance. One thing to notice here is variance is not the measure of spread, it's actually proportional to the spread. So this is the variance. Talking about the formal definition of covariance is a measure of how much two random variables change to get together. It indicates the direction of the linear relationship between the x and y. So the covariance tells us what is the direction of linear relationship between the x and y, whether it is positively positive relation or whether it is negative correlation. Either it it is having no relation. So it tells the direction of linear relationship between the x and y. So the formula is covariance of x and y is divided by 1 by n summation of I to n, where n is the number of data points, and x minus x bar, where x bar is the mean of x and y bar is the mean of y. X and y are individual data points. So the question comes here is, what was the need of covariance when the variance exists? So the variance is only single axis metric, means it applies to only one variable, whereas the covariance applies to the two variable, and the variance tells only the spread of the values. It doesn't tell how the two variable vary together, means whether if one variable increases, whether the second variable decreases or not. So it doesn't tell how two variables vary together. And the variance tells us how far it is from the mean, and it tells the direction of the mean. So to better understand what was the need of variance, uh, we can take the two data set which will be having the same mean, same variance, to understand why we need the metric called covariance. So let's start with the data set. I've taken a simple data set, like I will be taking some. Let's plot it graphically first, and then we will take the data set. So this is data set A, and I will be taking another data set B. Here I will be plotting uh, like -3, -3. Let's take 1, 2, 3, 1, 2, 3. The coordinates x and y, here 0 and 0, here -3 and 3. And when it comes to here, 1, so these coordinates are -3 and 3. Here it's 0 and 0. Here it's 3 and minus 3. So by looking at the data set itself, we can say that the data sets vary in the distribution and in the nature also with this. So when we calculate the mean of both the data set, like mean for x is, let me write x and y, x, y. This is for data set A, and data set B, x and y. So minus 3, 0, minus 3. So if you find the mean of x bar equal to, it will be 0 because minus 3, here it's plus, I think. Yes, it's plus. So it will be 0 for this also, and it will be for both the data set, the mean of x will be 0 itself, and the mean of y for data set A will be minus 3 plus 3, it will be 0, and for B the mean will be, it will be same, it will be 0. So the mean for x for both the data set, and for y also for both the data set, is 0. So here we can see that even though mean is same, but we have different nature of the data in the graphical. So let's calculate the variance in the second. Variance. So the formula of variance is 1 by n summation of xi minus x bar whole square, and this is respect to the x, and variance of y is same 1 by n summation of y I minus y bar whole square. So if we calculate with the this formula, we will be getting the variance of x as 6. We will be getting the variance of y as also 6. So how do you differentiate between these two data set? Because these two data set in the graphical and visual are different, but we are getting the mean and variance same for the both the data set. Here also it is 6, here also it is 6. So but when we calculate the covariance between covariance of these both the data set, we will get a clear picture of why there is need of covariance. So let's calculate the covariance here. Covariance. So the formula of covariance, which I showed earlier, is covariance x and y, then 1 by n, where n is number of data points, then summation of xi minus x bar, and then summation of yi minus y bar. Xi is the individual point, yi is the individual point. So I will be calculating the covariance for only one data set. You can calculate it for data set B also. Data set A. Let me write x, y, and xi minus x bar, then yi minus y bar, and then the product, because we need product. So it's minus 3, here also it's minus 3. Yes, and then 0, 0, 3, 3. So xi minus x bar will be, as the mean is 0, we will be getting the same values, minus 3, 3, and in the for y also we will be getting minus 3, 0, 3, and the product will be 9, and here also 9 and 0. So this whole will be 9, and n, in terms of n is here. The covariance which we will be getting is 1 by n is 3, and the product which we are getting is 9 plus 0 plus 9, which will be 18 by 3, which will be 6. So the covariance for dataset A is 6. When we try to find, let me try to find dataset for dataset B also, where x, y, xn minus x bar, yi minus y bar, and then the product here minus 3 0 3 3 0 minus 3. And when we calculate xi minus x bar, because x bar is 0 itself, we will be getting the same values, 3 0 minus 3, and the product here is, we will be getting minus 9 0 and then minus 9. So when we calculate the covariance for dataset B, we will be getting 1 by 3, which is number of data points, then minus 9 plus 0, it's minus 9. So it will be minus 18 divided by 3. The covariance will be minus 6. So this is the difference. For dataset A, we are getting the covariance of 6. For dataset B, we are getting the covariance of minus 6. Why? From the dataset itself, we can clearly understand the dataset is positively linear relationship, because if one variable increases, the other variable also increases. But in the dataset B, it is there is negative linear relationship between the x and y, because if one variable is increasing, the other variable is decreasing. So this is the problem that covariance solves. We will be getting the nature of relationship between the two variable with the help of covariance. So one thing which I want to mention here is the covariance does not tell the strength of the data, a strength of relationship. It doesn't tell the strength of relationship between the two variables, but strength of variation between the two variables, because it is affected by the scale of, data points. So it doesn't mean that if the covariance is large, it means the relation is very much correlated. It The covariance only tells about the nature of relationship. If the covariance is positive, then these are linearly, there is a linear relationship. If one variable increases, the other also increases. If there are negatively if the covariance is negative, then we can say that the linear relationship is negatively linear relationship. If one variable increases, the other variable decreases. So only we will be getting the nature of a linear relationship, not the strength of relationship from the covariance. So to address this issue, we will be having another one metric, which is correlation. We will be using the correlation. While this correlation doesn't have a lower and upper bound, it can be anything from minus infinity to plus infinity. But whereas the correlation, it will be only ranging from minus 1 to 1, where 1 is very highly correlated. The strength of correlation is very high, where if the value is towards the minus 9, then we will be getting, means these are negatively correlated. So even in the Python, when we are plotting the heat map, we will be getting the correlation itself with the each of the variable. If there are some attributes, we will be getting some number which will be correlation itself. That is correlation itself. So let's find the correlation between these two data sets now. So the formula of correlation is very simple. the correlation of x and y, we will be calculating it by, we will be having covariance of x and y, then we will be multiplying by standard deviation of x and y. So we know for let's take the first for data set a. uh, in our data set a, we can see that it is positively correlated. What was the covariance of x and y? The covariance of x and y for the data set a was 6. And what is the standard deviation of x and y? as we had as we had the covariance of 6, when we standard deviation is nothing but the square root of variance. What was our variance for data set a and b? It was 6 for both the data set and both the x and y. So if we do and to root, so we will be getting 6 by 6. So the correlation which we are getting for data set a is 1, and for the data set b is, what was the covariance between the both the data set for the data set b is -6, and it will be same, root of 6 then root of 6, we will be getting -1. So this is showing the strength of a relationship between linear relationship between the two variable. Now we understand why there is mean, why there is variance, why there is covariance. To tackle the drawbacks of variance, we will be getting the covariance, and the covariance only tells the direction of the linear relationship. There is a metric called correlation which tells us the strength of relationship between the two variables. The more it is towards the one, the more it is highly correlated, positively correlated. The more it is towards the -1, it is weakly correlated, we say. Negatively correlated negatively correlated until 0 to 1, it's positively correlated. Until 0 to -1, it's negatively correlated. And the more it is towards the 1, it is weak, and more it is toward the extreme, it is very high, we can say. So as here also we can say that it is very highly correlated for data set. That's why we are getting the correlation as 1. For here we are getting the correlation as -1. So by this, I think we got the idea of what is correlation and everything behind the covariance and correlation. So let's move on to the correlation. The same definition here I have pasted. The correlation is a statistical measure that describes the strength and direction of the linear relationship between the two variables. It is the normalized form of the covariance, meaning it removes the influence of the units and the scale, allowing for easy comparison between the different variable pair. So here we can see that the data points are very much perfectly positive correlation has been shown. The correlation is 1, and there are weak correlation, sorry, strong positive correlation, because it towards the 1 itself, no. And if the correlation is 0.5, then we can say that there is a positive relation, but there is a weak positive correlation. And if the points are scattered like this, then we can say that there is no correlation between both of this. And here we can see the negatively correlation. If the strength of negative correlation -0.5, here it is given. So this is weakly negative correlation. Here we can see the points are very close to each other, so we can see there is very strong negative correlation between among the variables. And if the correlation is -1, we can say that it is a perfect negative correlation. Means if one if one variable is increasing, the other is decreasing. So the formula of covariance correlation which we saw earlier. So One of the most concept to be understand in the statistic is the correlation and causation. So the correlation does not imply that a causation. So uh, the word itself means the correlation does not mean the causation. Means that just because two variables are associated with each other, it doesn't necessarily mean that one causes the other. In the other simple word, I can say that correlation between two variable does not necessarily imply that the one variable is the reason for other variable behavior. So so let's take a real life example, which can make us understand better about the correlation and causation. So shark attacks versus ice cream, there was a positively correlation between this in the summer. So one might think that if the sales of ice cream was high, the shark attacks also was more. But if we see, there is no relation between both of this. But we have a positive correlation. It doesn't mean that eating more ice cream is eating so it doesn't mean that having more ice cream sales doesn't mean that we are having the shark attacks. So here we can see during summer months shark attacks increase, ice cream sales also increase. These two variables show a positive correlation. So the main idea which I want to share is, because just because the two variables are highly correlated or a positive correlation, it doesn't mean that one is affecting other. So what misinterpretation can be taken from this positive correlation is buying ice cream causes the shark attacks. So some of the this is some of the misinterpretation from which we can take it from the correlation. But it's completely false. There is no direct causation between both this. So there must be a third variable which is causing that. So after study what was happening, that the third variable was involved, like summer, there is in the summer. So in summer, hot weather, more people go to beaches, obviously, because in the summer, because of the weather, they want to swim and all. So when they go to the beaches, more chance of shark attacks, because the number of people in the beaches will be high at summer itself. And because of hot weather, people were buying more ice cream. So this was the theory behind this shark attacks and the ice cream sales. So we should not assume the causation that one variable is causing other variable if there is positively correlation between both the variable. So the key lesson is shark attacks and ice cream sales have correlated, but one doesn't cause the other. This example perfectly shows why correlation uh, is not equal to causation. The danger of making assumption without considering the external factors is huge in terms of the business perspective. So so now you know how covariance helps us measure the relationship, and how correlation gives us the direction and strength. But remember, correlation doesn't always mean the causation. I hope you found this video very helpful. If you did, don't forget to like, comment, and subscribe so that you don't miss the next one. In the upcoming video, we will be talking about the probability distribution, specifically probability mass function, probability density function, and how distribution shape our understanding of the data. Thanks for watching, and I will see you in the next one. Until then, keep learning.